welcome back, guys. We need to do this problem. So we need to prepare a power plant or to design a power plant that has certain conditions, okay? So the most important one is about this efficiency, okay? So the efficiency needs to be higher than 30%, okay? That's one of the requirements. I would say the most important condition. Also, we need to get the maximum pressure 4.5 megapascals, and the minimum pressure should be around 100 kilopascals, okay? Another conditions that they are giving us is that the efficiency of the turbine needs to be 85%, and the efficiency of the pumps, if there are many pumps, needs to be 65%, okay? So after that, you're free to choose whatever you want. That's kind of the idea for this problem. And it's not an easy problem, okay? And you will see why. So I will try to do this as naively as possible and say, well, you know what? I'm going to take this simple Rankine cycle here, and I will try to do this problem, and then maybe I can achieve this efficiency of 30%. But you will see that it's not very easy. You can you can propose several schemes of a Rankine cycle, okay? And you will see that you need to improve this Rankine cycle in order to get to this 30%, okay? You will see why. Okay, so let's just go with this. So for one, it's at the outlet of the steam steam generator. I will propose that P1 equals my 4.5 megapascals. Meanwhile, my temperature, I will put it as 600 degrees Celsius, okay? So 600 degrees Celsius is a really high temperature for steam. You can go higher than this, but it's like a not really well explored environment, such a high temperature. But you will see later that I'm gonna cheat in this problem. Okay, so with this data, I will get that my enthalpy, it's around 3, and then my S1 equals to, let me just see where are these numbers, because I already have them here. So this is 3,670.9, and this one is around C3 7.3127. Okay, so that's about it. Now I have already here for these guys. And okay, let's just go with 2. So 2 needs to be stayed as 2. This is 2s, which is the isentropic part, and 2r, which is the real part. So I'm going to go with the isentropic part. S1 needs to be equal to S2, otherwise it's not isentropic. So I will put this same number here. And also P2 equals to 100 kilopascals, okay? So with this information, you can go into a calculator, you can go to your steam tables and check if this is gonna be a mixture, okay? So this guy is gonna be a mixture. Actually, if you want to know this, so the quality of this isentropic state there, it's gonna be equal to 0.992. Okay, so that's kind of the idea, and therefore H2S for this point is actually equals to 2,657.78. So I'm gonna go fast, because otherwise it's too elaborated of a problem. Maybe you need to know how to get these points. Okay, now after that, what I'm gonna do this, you can actually get the isentropic work performed for the turbine when it goes from 1 to 2, okay? And I would say for 1 to 2s. So this would be the isentropic work produced by the turbine. Okay, so in that case, you will know that this is H1 minus H2s. But remember, we have an efficiency for the turbine. Therefore, the real work, okay, in order to get to that point, we need to do the efficiency of the turbine multiplied by the isentropic work going from 1 to 2s, okay? So after this, I will try to put this information here. And if you do that, you will get here that I have this value, 861.14 kilojoules per kilogram, okay? You can actually get these numbers, you can put it here, and you will get the isentropic. And then if you use the efficiency, you will have a real value for the turbine, which is actually less than the isentropic value. Got it. So I already have this information there. Let's just go with other points. So 3, okay, so 3 needs to be saturated liquid. This is going to be saturated liquid, and the pressure is still 100 kilopascals, because in a condenser, this is a condenser here, you don't change. It's an isobaric process, so you don't change pressure. So after this, you will get that H3 equals actually to the saturated liquid enthalpy at the conditions of 100 kilopascals. So I'm gonna just go put it here, and H3 equals to so what I would get here is where the hell are you? Okay, so because I have a bunch of numbers here, so it's not very easy to locate them. This is the enthalpy of this saturated liquid going at 3. And with that, I will put, now let's just go to this 4. And after 4, you need to decide if this one is an isentropic point or a real point, because this guy over here, which is a pump, has an isentropic efficiency, which is this one. Therefore, you need to take that into consideration. Fine, let's just do the isentropic point at 4, and this one would be equal to H4S minus H3 is going to be equal to B3 multiplied by P4 minus P3, which is a typical way to calculate things after a pump. So if you do that, this is actually the work of the pump, pump, as P is pump, and at the isentropic part. Okay, so if you do that, this one is going to be 0.001043. This is actually happening at this state. Okay, so how do I get this specific volume? This specific volume comes from this state at 3. Okay, and then I'm going to do, well, you know what? I have kilopascals, that's the maximum pressure, minus the minimum pressure, minus 100 kilopascals. Therefore, my WTS, I'm sorry, again, WTS, this is not the turbine, this is the pump, okay? So the pump, for the isentropic part, I actually do not care too much about the isentropic part. I actually care about the real part of the pump. And if you do that, you can calculate it pretty easy, and you're just gonna do PS divided by the efficiency of the pump, which is gonna be a higher value because you spend more electricity in a lousy machine or in an imperfect machine instead of the isentropic machine. So if you do that, you will get that this guy's going to be 7 point, where the hell are you? Yes, 7.0603 kilojoules per kilogram. And meanwhile, if you want to know this number, this one is going to be 4.5892 kilojoules per kilogram. Okay, got it. So now we have that. Whew, okay, I have established all my points. This one, 1 and 3 does not depend on they are isentropic or real, but 2 and 4, yes, those points depend on whether they are isentropic or not. Okay, so I have already got all those information. Now, the only thing that it's missing here is to get all the information, because finally I want to know if I achieved how much is this number. So this number is going to be the net work, okay, the net specific work divided by the specific heat introduced in the steam generator. Okay, so if you do that, you will get that this is H1 minus HO3, the real part, minus, because you need to subtract something from the pump, and from the pump is going to be H4R minus H3, and this is going to be divided by H1 minus H4R. Okay, so if you introduce these numbers, you will get that this efficiency is actually 0.2631. So if you see now, you have used a really high temperature, this one, and still you cannot get to this 30%. So something must be done here. Okay, so you need to improve the efficiency of this Rankine cycle, and there are several ways to do that. And you can do little by little. You're introducing one improvement and then another improvement and then another improvement. I mean, you can cheat a lot in this problem and say, well, you know what, instead of the 600 degrees Celsius, let's just do 1,000 degrees Celsius. But actually going to around 1,000 degrees Celsius of steam inside this pipe for this steam power plant, it's not very realistic. Okay, it doesn't mean that you cannot have it, but it's not the typical way that you introduce steam into a steam turbine, okay? So that would be cheating in a bad way. So let's just cheat in a better way. What I mean by cheating is that, well, okay, let's just improve this stuff, okay? So if you see here, this is a steam power plant that has several features as improvements, okay? One of them is the reheat. The reheat means that you will introduce the steam that you got into the steam turbine. This is a steam turbine. This is a steam generator. This is pump 2 and this is pump 1. This is the condenser and this is a mixer here. So this is just a mixer. Okay, so let me just tell you about this line over here. This one is called reheating part. This is a reheating part. What you just did is was just to introduce steam that was inside the steam turbine and you put it again into the steam generator in order to, introduce a little bit of heat there. So the point three has higher enthalpy than point 2. That's kind of the idea. And then you introduce these 3 again into the steam turbine so that it's still producing more power, okay? And now you put it again in 4, okay? So you put it out at 4, then you go into the condenser, then you get the pump. So far it's the same thing as a typical Rankine cycle, but I have also introduced another improvement, and this is called the regeneration, okay? The regeneration means that, okay, I'm gonna use a certain amount of steam, okay? Not the whole deal, but a certain amount of steam that I will call Y. And in this case, Y equals to M going at, okay, so at this point, I don't know how to call it, okay? So from the mixer, I'm gonna call it from the mixer. I'm not going to use that one, but no problem. And this one divided by M1, okay? So M1 is a total amount of flow rate or mass flow rate of steam going into the steam turbine, okay? And then I'm gonna just put out a fraction. So this is just a fraction of an amount of flow rate that I'm gonna introduce into a mixer. So the whole thing with the mixer is to heat a little bit or to increase the temperature of the water that is going to go into the steam generator, okay? So I'm using heat from steam, okay, in order to increase temperature of this feeding water into the steam generator. That's kind of the idea, okay? So take a look at this. If this guy is Y, this guy is going to be 1 minus Y, okay? So I have used a certain amount of steam going into the mixer. Therefore, this line over here is actually 1 minus Y. So here you have the whole deal, M1, just the complete one. And then you just put some steam into the mixer. Therefore, you just got the 1 minus Y. So this is again 1 minus Y. This coming into the steam turbine is 1 minus Y. Therefore, this guy is 1 minus Y. So I think you get the trill. So you get over here, this is 1 minus Y. And therefore, here you have the whole thing again. Going out of the mixer, you have again recover this amount of steam that you put out from the Y line, okay? And therefore, this is also M1. The whole thing is going down over again. It's a little bit, elaborated, and it's not very clear maybe at some point, but that's kind of the idea. And also, I'm gonna cheat in some other way. So I'm gonna use another color for this one. Let's just use blue. And so for this one, I'm gonna say, well, you know what? For one, I'm gonna get this 4.5 megapascals, which was a condition, but I'm gonna increase a little bit temperature. It's just in order to get there, get where? To get to the 30%. That's kind of the idea. That's what I'm doing here, okay? So if you use these numbers, okay, I'm gonna try to do this fast. Remember, you can go little by little. So instead of, putting reheat, this thing has a reheat section and it also has a regeneration. Oh my God. Okay, so a regeneration part. You can go, well, let's just try with the reheat part, just with that. And you will still find yourself struggling to get the 30%. What about regeneration? Well, let's just do both, okay? So in order to increase a lot the efficiency. I don't know if you see here, but the greatest villains in this story, the obstacles, the largest obstacles here are these two guys. If these guys were kind of perfect, closer to one, I would get to the 30% in an easier way. I wouldn't need a lot of, of these improvements, this reheat and this regeneration. I wouldn't need them, or I wouldn't need a lot of that. Okay. But since these guys are performing poorly, 85% and 65%, therefore, that's why I'm struggling so much in order to get to this 30%. That's kind of the what's happening here. Okay, so let's just put all the information there. And again, let's just do this big one. So what I'm gonna do here for this big one, I already have it here. So this is H1 equals to 3,903.3. Meanwhile, the entropy for this fella is 7.5647. Okay, I'm gonna use all those numbers. See, there's a lot of much more points in this diagram, so let's try not to be confused with those ones. What else? So that's one. Okay, now let's just go to the 2s. 2s is gonna be this fella over here, but the isentropic part. So for the isentropic part, I will say, well, you know what? I'm gonna put out this steam at 2 at this pressure. So this one over here, it's just my option. This I just chose this one. Okay, so this one, you can change this number. Nobody's telling you, well, you know what, you should be, I know, you should put it at 2 megapascals, or you should put it at, I don't know, 500 kilopascals or something. This one for me is just, I just said, well, you know what, I'm going to put out this steam at 2 at these conditions of pressure. Now, also, I need to know that S1 and S2 needs to be the same one, otherwise it's not isentropic, so 7.5647. And with these two informations, I will get right away, you can go into a calculator, that H2S equals to 331.21. Okay, so that's kind of the idea, kilojoules per kilogram. And you know the drill, you can do your isentropic work for this one, for this part, and this will get you 573.009. I'm not going to put these units, okay, so just not to waste some time. And then I'm going to do the real part, and the real part, you need to multiply by the efficiency of the turbine, which is the same one. And if you do that, you will get to this number, which is 487.18 over 12. Okay, so you have that part. Therefore, if you want to know what's going on, so this one is just the work, the real work. Therefore, you can get from here the H2R that maybe you will need it later. So this is 3,416 and then 0.17. Okay, so that's the efficiency. No, this is not the efficiency. That's the enthalpy for the real point at the outlet of the steam turbine that is going into the reheat part. That's kind of what is going on here. Okay, so that's the drill. Now let's just go with 3. So for 3, it's after receiving heat from the steam generator in the reheat part. So I'm still gonna get 1 megapascals because the pressure hasn't changed. And also I'm gonna say, well, you know what? My temperature is gonna be the same one as 1. So this one has a 700 degree temperature. And this point, I'm gonna say, well, you know what? The steam generator does the same for this line that is going in the reheat part. So if it's doing this, so I will get here H3 equals to, I think I have the numbers here and I already have them. This is 3,924.1 kilojoules per kilogram. Okay, and also I'm gonna get the entropy because I'm gonna need it later, because it's gonna go into the steam turbine again. And if it's gonna go into the steam turbine again, I need to use the isentropic efficiency of the turbine. Okay, so I have these two guys. I have the enthalpy and the entropy. This one is really important. I'm gonna use it maybe later. Let's just go with 4S. Now for 4S, it's the outlet of the steam turbine after the reheat part, okay? And it's going through an isentropic process from 3 to 4 But remember, 4 has now 4S and also 4R, okay? And we need to get both of those points. So that means that S3 equals to S4, which I already have it here. I'm not going to write it again. And also pressure. So pressure for this point is equals to 100 kilopascals, which is our condition of minimum pressure. And if you do that, you will get to superheated steam, actually. And this guy, I think I got it. So let me see if I can find it here. Yes, I can find it here. This is 3107.8. Okay, so after that, I actually can get this point, but I'm not really interested about getting the isentropic work from 3 to 4. I'm actually interested in the real part. So if you do the real part, you will get to this point. This is the isentropic efficiency of the turbine, 3 going to 4S, okay? So the isentropic work. And this guy, I think I already have it here, equals to, I'm just gonna put it here, equals to 693.855, oops, kilojoules kilogram, okay? So that's kind of the idea when it comes from 3 to 4. I mean, I can get this part because I mean, you can use H3 minus H4S and you're gonna do the isentropic part of the work, but I'm interested about the real part of the work because that's what I'm gonna use later, okay? So if you notice now, I have already got, you know, the first part of real the real steam turbine work going from 1 to 2, and the second part which is going from 3 to 4 in the steam turbine, okay? Both of the real parts doing that. Okay, so I have these numbers, and this is actually the real power, or I mean the real specific work that the steam turbine is doing. Okay, so far I think I have solved the problem that has to do with the steam turbine. Okay, but that's not the only part. Let's just go with some other parts. So for example, let me just see if I can do 5. So for 5, it's the same thing that it's been happening before. So I'm gonna do saturated liquid here. And what else? So 5, it's gonna be, okay, yeah, P5 equals to 100 kilopascals, 100 kilopascals. So it's the same thing happening in this condenser. Things has not changed there. Okay, so I already have this information, and this one is gonna be the 417 that I already used back in the simple Rankine cycle. And with that, okay, so I already had this information here. Let me just see if I can get a 6x, the isentropic part of this point at 6. Let's just see if I can do it. So this is H6x minus H5 equals to B6 multiplied by P6 minus P5. And okay, so this guy, I already have it. I already use it actually in the other steam turbine, in this other steam Rankine cycle. And P6 is a little bit tricky. Take a look at this. So I'm taking this line from here, from the steam turbine. I already decided that this reheat part, it's at 1 megapascals. So this mixer is actually at 1 megapascals. All flows going into the mixer or going out of the mixer needs to be at that same pressure. Otherwise, they do not mix. Okay, so it's a 1 megapascal mixer. So this 6 over here, the pressure should be 1,000 kilopascals because it's 1 megapascal minus the pressure of the condenser, which was this one over here. So if I do that, I will get my 0.9387 kilojoules per kilogram. That's the isentropic work of the pump. I'm not interested about that. I'm interested about, let's just do the first real part of the pump. This is pump 1. Okay, so the real work doing by that this pump needs, sorry. So it's just P1S divided by the efficiency of the pump, which we already know this one. Therefore, this one is pretty easy, 1.444 and kilojoules per kilogram, that I'm not going to put the units, okay? So if you want to know what's going on, so I can get from here H6R, which is this guy over here, 94 kilojoules kilogram. Okay, so that's another important enthalpy that I may use later. That's kind of the idea. So let me just put which enthalpies are important here. So far, I think I have all of them. This is H4S. I didn't get H4R, which was a mistake from, let me just see if I can find it around here. I don't think I can find it around here. Well, okay, so hopefully I don't need this H4R. I mean, you can calculate H4R, right? So if you do this one, this is the same thing as H3 minus H4R equals to 693.8555. You already have this fella. You have this fella, of course, and you don't know this guy, so you can get it. But I think I don't have it here. I don't want to waste time, okay? So let's just go to another important part. What about this 7? Okay, so 7, it's find out with a little trick. It's not a really nice trick, but it's an important thing to know, okay? So I need to know also, I want to know, for example, H7. That's an important thing here. I want to know H7, but it depends on several things. So I'm going to do for the mixer part, maybe you know regeneration, it's not a problem, but maybe you don't. So this one is 7, this one is 2, this one is coming from here, ups, and this one is 6, right? So this one is 6. Okay, so you can do this stuff. So M7H7 equals to M2H2 plus M6H6. So this is just a simple energy balance into this mixer, okay? So that's what you're doing into this mixer. Now let me just divide everything by the M7, M.7. So if you do that, H7 is gonna be equal to YH2, hopefully you know Y, plus 1 minus YH6, okay? We already have solved this H6R. We know how much this H2R is this one, but we don't know this fella and we don't know why. So we can in a problem. Okay, so this is the trick here. If I'm gonna introduce this 7 flow into a pump, it needs to be at least saturated liquid. So I'm gonna force this guy. So 7 needs to be forced to be saturated liquid. Otherwise, it cannot go into the last pump or the second pump. So I'm going to say, well, you know what? Saturated liquid, okay, at the pressure 1 megapascals. We established that 1 megapascals is the pressure of this mixture, okay? So if you do that, I'm already deciding how much is H7. So H7 for this part is, you can go into the steam tables in order to find this 7 number. And if you do that, you will find out that this one is 761.39 kilojoules per kilogram. So you already have this guy. Now your only unknown is this Y. So the Y is an unknown, and it will tell you how much steam you need to get out of the steam turbine in order to do the regeneration part. Okay, so it's an important thing to understand there. Okay, so if you do that, you will get H7 minus H2 minus H6R divided by H2R minus H6R. You can get it from here. It's just algebra. It's just algebra going on here, and you will get this expression. So you have everything you need in the right side of this equation. Therefore, Y equals to a really small amount, so 0.1126. So it's telling you, you don't need to get a lot of steam from the steam turbine, okay? Because otherwise you will get into problems with the second pump. Otherwise you will not get it to saturated liquid, okay? So finally we got this value of Y because it was open here. Well, you know what I said about the Y part and this 1 minus Y, but how much is Y? Well, now you know how much is Y just because of considerations of the second pump. I need to fix this pointer, okay? So with that, now I know the fraction that I need to put out from the steam turbine in order to do the regeneration part. Okay, so that's something that was an important thing to do. Now let's just go with okay, so for 8, I'm sorry. So for 8, okay, so 8, let's just see about 8. 8s, okay, so HO for the isentropic fella, it's gonna be like this, P7, P8 minus P7, 7. So this is the isentropic part, okay? And if you do the isentropic part, you already, I know you don't have this one, so you need to get it. So V7, it's BF, or the saturated, the specific volume is saturated liquid, multiplied, no, at the conditions of 1 megapascals. Okay, so this guy, it's gonna be equal. Let me just see where the hell I have this fella. And this guy is 0.001127. Okay, so now that you're gonna do the whole thing, so the pump to, but the isentropic work is just this, and you will put 0.001127 multiplied by P8, which is just this one, minus 1,000, right? Because P7 is the pressure of the mixer. Therefore, this is, I think I got it. This is 3. But you remember that you don't really care about the isentropic part, but nonetheless, let me just put it. And if you do that, let's just get the real part. So the real part is going to be this fella over here, the isentropic divided by the efficiency of the pump. So this guy will amount to 6.06046 kilojoules per kilogram. So that's about it. Okay. And you can also get the H2R here, H8R. You can also get it. And it's actually H7 plus HP2R. Okay. And this fella is going to be equal to 767.458, okay, kilojoules per kilogram. This one is an important one because it's going to go into the steam generator, okay? Good, and I think I have solved all the points. It's a little bit tricky, so I got you with that one, okay? It's not very easy to solve. This is actually a nice, fun problem because it's too elaborated, okay? So far, we haven't proved that this guy is above 30%. We haven't proved that. We just hope we can get to that point, okay? So now let's just try to do that. So I'm going to use another color. The efficiency of the thermal cycle needs to be net divided by Q in. So this one is a little bit more complicated, so let's just go with that, W net. Okay, so it's going to be the real part of the turbine minus P1R minus P2R, okay? So the divided by the works of the pump, but the real part. Everything's about the real part, okay? Q in. So Q in is an important one. It's going to be H1 minus HOR. Got it? This is the first pass from going from A to 1, okay? But also, I'm putting out heat right here, okay? So this one is gonna be plus 1 minus Y, okay, H2R, I'm sorry, backwards, H3 minus H2R. This is the reheat part. This is the simple traditional part going from the feeding water to the outlet of the steam generator. And this is the reheat part. And I need to also specify this, okay? This is an important guy because not all of the mass flow is going through it, just a part of that. How much? Well, 1 minus Y, because a Y part I used for the regeneration part. Let's just go with this one. So the turbine is actually using the difference of enthalpy H1 minus H2R, okay, plus a second part, which is this 3 to 4, okay? So this H3 minus H4R, but remember, not the whole flow is doing that. So I need to specify that only that amount of flow is producing this real power. Okay, now what about the pumps? Well, P1R is going to be equal to H, let's just see where the hell you are, from 5 to 6, but just this amount of flow. So H6R minus H5 multiplied by 1 minus Y. We already had this number, okay? We call it the specific word, but now I need to introduce that not the whole flow is going through that pump, okay? Now let's just do P2R equals to, this Y is going to be H8R, my God, minus H7, okay? and multiply by the whole thing. I think, yeah, everything here is the whole thing. Okay, so with that, I already have established everything I need. Everything is here. I'm not going to put the numbers there, but I'm going to tell you that we have done it. 0.305. Okay, so that's what happened there. We already established that. I think that the only shaky part in this problem is not the reheat part. That's perfectly valid. Not the regeneration part. Perfectly valid. The only thing that could be a little bit shaky if I was your professor is actually this one here, this 700 degrees Celsius. I mean, I know what you did that because you want to get to the 30% of the efficiency of the cycle, okay? So that's why you're doing this 700. The thing with this 700 is not a lot of power plants actually design that the entrance of the steam into the steam turbine should be around 700 degrees. It's too high. It's actually not ridiculously high, but it's a little bit high for traditional purposes. So far, it's just an exercise, a numerical exercise, and we got it. Okay, we actually fulfill these requirements. One more thing to say, okay, let's just see how this thing looks in a TS diagram. So this one is a T, this one is the S. Let me just move myself here. And I'm going to put it here, this curve here. Okay, so for this one, I have three pressures. I have the maximum pressure, okay? This maximum pressure is 4.5 megapascals. Got it. I have an intermediate pressure, which is 1 megapascals, is the reheat pressure. And I also have a real small pressure, which is the minimum pressure of the requirement. So I'm going to put it here, 1 megapascals, and this one is 100 kilopascals, okay? So those are my three pressures there. At the outlet of my steam generator, I am around here. This is 1, okay? So this one would be 2S. This one over here could be 2S because that would be my isentropic part, and this guy is the entropy. Therefore, it would be a vertical line. But since I'm doing things in the real part, this is going to be 2R. So this one is 2R. Got it? Okay, so after 2R, I could be doing things like this if this was isentropic, but I'm not doing that. So this guy is going to be around here. This guy is actually here. This is 4. No, I'm sorry. Which number is this one? So 4, yeah, it was 4 after the steam turbine. So this one is 4R. Okay, so I have another point here. And all of these 1, 2R, 4R are a little bit moved to the right because things are not isentropic. Okay, that's actually what's happening there. Okay, from here, from the last part, I go into the condenser, and into the condenser, I'm losing a lot of heat, and I get to this point, which is 5. So this point over here is 5. Okay, got it. And then comes into a pump. So this pump is gonna elevate the pressure to 1 megapascal. So I have here my 1 megapascals, and I should be doing things vertical if this pump was isentropic, but it's not isentropic. Therefore, I'm going to move it a little bit, whoops, to the right because it's not isentropic. So I got here to my 6R point. Let me just check if that's correct. Yeah, this is 6R because it's at 1 megapascals and it's coming from 5. So far, so good. Now the mixer. So the mixer is a little bit tricky, right? So the mixer is said, well, you know what? From here, I got this. This is a white flow. So I took a little bit of flow, okay, and put it and mix it with this 6R. So I'm mixing, hopefully you can get this one. So I'm mixing 6R. This is 6R going into the mixer. 2R is coming into the mixer, okay? So 2R is coming into the mixer. So I'm actually mixing this 2R with this 6R. And in the middle, it's going to lay the 7 point. In the middle? Well, yes, this 7 point is a result of mixing 2R with 6R. And it's like, well, okay, so somewhere around this line, I need to put 7. And I don't know if you remember, but I established that 7 should be located at saturated liquid. So this guy over here is 7. I decided that 7 was to be located here. Saturated liquid at 1 megapascal. I decide that. So I found how much Y I need to take from 2R so that I get to this 0.7, okay? So that's one way to solve it. It's not the only way. And after that, I'm gonna go into a pump. Let me just put it black again. So into a pump that, whoops, that it's moved a little bit to the right. It shouldn't be perfectly vertical. It's actually moved to the right a little bit more, okay? But so far, let me just put it that way. And in that place, it could be this 8R. This is the 0.8R. Okay, guys, so that's how this thing would look in this type of diagram. That's what's happening there. I have a reheat, but I'm sorry, this is so wrong. Oh my God, this is so wrong. This is one thing is really missing here. So the regeneration part is perfectly done here, perfectly depicted here. There is one big mistake here. The reheat part, I haven't put the reheat part. So let me just put the reheat part. So I have one going here. So why it's being used in green into the mixer part, so that's correct. But then comes the reheat part. And the reheat part, what it will do, okay, so I'm gonna go from 2R, and then I'm gonna increase, okay, so I'm gonna increase, whoops. Let me just take this out because otherwise it wouldn't be seen there. Come on, eraser. Okay, okay, like this. What the hell are you doing? Oh, I'm gonna tell you why. So I need to increase this line over here. Okay, got it. And I'm gonna move it around here. So hopefully you trust me, okay, that this is 700 degrees Celsius because one was located at 700 degrees Celsius. Now I can put the 4.5 megapascals. This is correct. This is where one is lying, okay? So what I have done is that I put it into a steam turbine and I got to 2R. Got it? So one piece of flow got into the mixer and another piece, 1 minus Y, I should say, it's going into a reheat part. And this reheat part will elevate the temperature up to 700 degrees Celsius, but the pressure, it's 1 megapascals. So this should be 0.3. This is actually 0.3 that I completely missed, okay? So what I'm gonna do here is erase a point. Okay, I'm gonna erase this point over here because 4R is not located there. Let me just put it where 4R is gonna be located. So this is 4R. Why? Oh, yeah, okay, because this 1 minus Y flow, 1 minus Y flow went into the reheat section, got into a 700 degrees Celsius, got it, and 1 megapascals, got it. So this is 0.3. Okay, I understand that. And then it suffered an expansion inside the steam turbine. So I'm expanding the steam up to 0.4 R. If this was a perfect turbine, it would get to 4S. Okay, but that's not what I have. So it just got to a 4R. So for this 4R, I'm located at 100 kilopascals. And this one over here is by using the efficiency of the steam turbine. And I'm located at 100 kilopascals and superheated paper. Okay, so that's actually what's happening. Therefore, the condenser is doing all this thing from here to there. Hopefully you can see that I'm doing, let me just do another, yeah, let's do condenser up, and all this line is what's happening inside the condenser. Okay, so now I have done this correctly. Okay, so now you have a reheat part and you have a regeneration part depicted in a TS diagram. Okay, so that's how it looks. Okay, guys, so I will see you later. Hopefully it was useful for you, and I will see you later.